In this video, I want to talk through progress I am making in trying to leverage the parallel interface bus that is a feature on the 65265 microcontroller. And my goal is to connect a pair of these 265s and have an ability to do private communication between those two without going to the main data bus and having to, contend with other things going on, and really be able to send this, whatever series of bytes of data using this private data bus between the, I want to call it the master microcontroller and a slave microcontroller. So maybe a little warning, first of all. I'll say that some of, or much of, I don't know, of the information that I'm going to share could very well be inaccurate. So take everything in this video with a grain of salt. I'm just sharing what I am learning up to this point. I think I'll have later videos that'll hopefully better clarify and maybe solidify some of my assumptions, maybe correct some of my assumptions at this point. And if, of course, you're watching this and I've not yet published a later video and you've got things that you can see that I'm not approaching correctly, do please drop me a note. Now, I'm trying to do my best. I'm taking information from the Western Design Center documentation. Probably the primary thing there is the data sheet for the 265. And it's got a lot of good nuggets of information, but it does not have enough to put it all together into a solution. And so there's a lot of reading between the lines or guessing or just experimenting that I'm doing to try to see if I can make this work. The other thing I'm using for a resource is Microsoft Copilot. Now, I've done a ton of Google searches, and there really is not much out there. There really isn't anything out there on this PIB, this parallel interface bus. But Microsoft Copilot does come back with stuff. So it does have sample code. If you ask it how to do things, it tries to describe things. And I've probably had a dozen different long-running conversations with Copilot running, and I get conflicting information constantly. I get inaccurate information constantly. So it's maybe 20% accurate. It's not real good, but it is giving me additional nuggets that I can kind of fold into my overall thinking about how this might work. And it's interesting, even stuff I was asking about yesterday compared to today, I'm getting totally different answers. And the answers I'm getting today seem much better. So things are changing, and I don't know how to explain that back on the AI side of things, but I'll take it for what it's worth. It's just things for me to think about, maybe things for me to experiment with, until I can find better, more authoritative information on some of this. So just the big warning here that, what I'm going to continue with definitely probably has problems, but at the moment, I don't have better information to tell me otherwise. So what is this parallel interface bus? And here's some information I'm kind of putting together to talk about it. It's really hardware. This is part of the 265 microcontroller. And it's really a way for me to have point-to-point communication between microcontrollers. So again, in my case, it's a pair of 265s. Now with this, I've got a dedicated 8-bit connection between the two microcontrollers, and there's hardware support for handshaking for that communication, which uses another port. So there's going to be 2 ports needed to make this work, 2 8-bit ports. That handshaking, all of the signaling between the microcontrollers, there's a bunch of registers that support its use. There's an interrupt specific to PIB. So all of this is part of the hardware as I understand it. Now with this, you should not need any external glue logic. You can have the 2 different microcontrollers on totally different clock sources, so independent clock domains. It's just a whole bunch of benefits to this. The idea of the hardware, though, is to make it really easy. You shouldn't have to do much coding. You should just be able to say, I want to store this byte of data, and the other microcontroller just gets it. But what I'm finding is that is not just that easy. And it comes down to lack of documentation, and I have more to learn. So the general communication is this, if I have two microcontrollers, maybe one of them I'll call a master, the other one I'll call a slave. The master says, I've got data, I want to send it to the slave. So it basically places a byte of data out onto one of the ports that is directly connected to the same port on the other microcontroller. It then has a way to signal to the other CPU through a different port, one of the lines. It says, hey, I've got data that you should take a look at. And it essentially drives pins to manage the signaling. It's also managing on both microcontrollers a flag register, kind of what's going on with PIB. And you can optionally use interrupts. And that's definitely the way I want to approach it, is to use interrupts. I can't imagine having something sitting there polling for the status to change. So interrupts is definitely the way to approach this. Now, I have not been able to get the hardware-based handshaking and data transfer to work. And in theory, it should be as simple as me writing a byte of data to a parallel interface register, or a PIR. I don't know if people call it PIR, PIR, PIR. I don't know what pronunciation is here, but I'll just say a PIR3, for example. There's a series of these. Now, I've tried that, and that doesn't work. And I think I have some things that maybe I'm learning that maybe this PIR3 isn't what I should be using, and I should be using PIR7. But I started out with, because the only thing I could find talked about PIR3, and that's the avenue I was going down when I started this. And for the life of me, I could not, when I wrote to it with my PIB enabled, could not get it to put out the right control signals or even the data on the ports that I would have expected it to put them out on. So from there, I said, okay, fine, let's go without the PIB. Can I essentially make this work and just validate that my connectivity is, in theory, acceptable between the two microcontrollers, and just see if I could. I was actually going for PIB with what's called a manual handshake. So you can either do an automatic handshake where the two microcontrollers will basically manage the handshaking between them on their own. Or you can say, I still want to use PIB, but I'm going to do a manual handshake. And then there's a third option that says, well, I'm going to do everything manually. I'm not going to take advantage of the actual PIB hardware, but I'm going to kind of do a parallel interface bus between my microcontrollers. And that's what I've implemented for this video. And through that, it's really helped me learn a lot and find a couple of pretty big issues with both my board and the Western Design Center board that will really mess up PIB if you're trying to make it work. Now, again, I'll put out the big asterisk here that's based on what I'm understanding. So later I might find that everything I'm telling you here is wrong, and that some of the modifications I've had to make to the boards really is not necessary, but we'll see. So I've got this PIB-like interface set up, and I'm just calling that a pseudo-PIB for now. Now I have ideas for next steps on the hardware-based PIB, and I'll come to that after this video. The next video hopefully will be me having the hardware PIB working, because I've got a couple of ideas since I got this current pseudo-PIB up and running. So the pseudo-PIB is definitely not my final target. It's really been just a way to learn and see if I can move closer towards a hardware PIB. So deficiencies of my current implementation as I go through this. First of all, I'm doing manual handshaking. So I'm not leveraging the native hardware that can potentially do the handshaking for me. Now, on one hand, I believe it's just native to the 265 ICs. There are two different packages, physical packages. So there's an older, like a PLCC package, and then there's a newer QFP package. It's like a 100 pin versus an 80 some pin. And the 100 pin is what's recommended for new designs. Now, I did get something back from Copilot at one point that said, well, possibly with the new package, the PIB really isn't functional in that package. I think that's unlikely, but I suppose there's a chance that there is something with the 100 pin QFP where PIB isn't actually functional. That I don't know. I haven't gotten it to work, so I can't disprove that for the time being, but I find that to be unlikely. Now, my implementation is going to do entirely manual handshaking. It's not going to leverage PIB registers. So that's one of the benefits, is that as different things are happening with PIB, from ready to send data to receiving data to interrupts, whatever, there are registers or a register or a series of registers that I might use to help me with all of that. I'm having to use an interrupt outside of the normal PIB interrupt. I'm going to use a negative edge pin 64, so port 6 pin 4, to handle on the slave an incoming interrupt request. That shouldn't be necessary. So I'm wasting an unnecessary pin, and I'm not able to just use the built-in interrupt capability of PIB. And what I'm doing is a lot more coding. It's not a tremendous amount of code, and you'll see that I'll walk through it, but it's still more coding. I should just be able to say store this data byte at PIR3, and the other slave should be able to read it. Now, again, everything I was reading up front or could find was saying, well, you should write to PIR3. You should do a store to PIR3, and then on the receiver, you read PIR4. That definitely did not work. That just even on the sending side, not even worrying about the receiver side. But then just today, I found information that said, oh no, you need to send on PIR7, and PIR3 is for receiving. So that's something that I have to test later. And like I said, I wanted to kind of finish this Pseudo-PIB before I kind of gut things and go back and try that. So here's a picture of what I am working with. On the left is the Western Design Center SXB board, handy little board, and it's got a lot on it. It's got the microcontroller. It has the FT232 for USB support. It has static RAM. It has a socket for external flash. And then it's got this port 4, 5, and 6 on the right side. And you're going to see that ports 4 and 5 is what I need to use here as I start working with PIB. But that also means you can't put anything else on those ports. And if there is built-in functionality on that system using ports 4 or 5, you need to disable it, not use it, whatever the case may be. Now on the right is what my board looks like. This is my custom 265 board. It's, again, almost identical to the board to the left in functionality. Really the only big difference, again, is I've put in a ZIF socket for the external flash instead of the PLCC socket. And I'm doing some extra decode for other peripherals that the 265 by itself can't do. And I'm running a faster clock. I'm running 10 megahertz for my Phi 2 versus the 3.68 on the WDC board. So ports 4, 5 are the two main ports that need to be used for PIB. So port 4 is used for control, port 5 is used for data. I'm also using a couple pins on port 6 and actually 3 pins on each of the boards. So on the master, the board to the right, which is what I refer to as primary, one of the pins I'm using to control the reset on the slave, or what I'm calling AV for audio visual. It's going to be my AV coprocessor on my next PCB, hopefully. So on the right, port 6, I'm going to take one of these pins off of port 6, which I've got sitting over here, and use that to connect up to the reset pin on this header up here so that I can control its reset state from the primary board. And then I've got some debug LEDs hooked up to a couple of the GPIO just to show me that my board is running, it's in its main loop, doing its cycling and not stuck somewhere. Now on the slave, I'm going to use the same port 4 for control signals, port 5 for data. You don't have a choice about that. Those are what PIB has to use. Now my implementation, this Pseudo-PIB, I could probably use any port pins I wanted to, but I believe when I actually get to hardware PIB, you have to use the pins that have been basically built into the hardware to support PIB. I'm also going to use on port 6 on the AV board a couple of pins for LED debugs, and also one that's going to receive an interrupt. Basically, it's going to sense a line being dropped and basically trigger an interrupt So it's an NE or negative edge. And let's see, 64, I think is what I was using on that. So port 6, pin 4. And then I, of course, need the reset line off of here on the left because it's connecting over to port 6 on my primary. So as I proceed into this, I'll turn my system on, and the slave or the AV system over here, I'm taking power from the power pins and connecting it to my master. And the master is where I'm feeding in power through a DC barrel connector. So that's what's powering everything. It just lets me control it better, see it better, run it from my workbench, my benchtop power supply, and not have to deal with a USB where the voltages can vary a fair amount depending on what I plug into. So I power that on, and the first thing that the master does, or the primary does on boot or on startup, is it holds the slave and reset. So it drops the reset line, just holds it down. So the slave has to just sit and wait until the master says it's ready. As the master's starting up, it configures all of its basically PIB related ports. So port 4, port 5, and in this case, PDD is the port data, which data direction do I want to go for each of the pins, and then also what actual data do I want to put on those pins for their default values when the system starts. And in time, I'll also enable PIB as part of that boot up sequence. But for today, I'm not enabling the hardware PIB. Once that's done, it actually releases the reset so the slave can start up. It configures its PIB pins. Now keep in mind the port 4 is connected to port 4. So whatever's output on the master should be an input on the slave and vice versa, or in a tri-state, a Z state type of thing where it's not input output. It's not putting anything out on the bus. Probably don't want two pins connected, both trying to drive what's on the interconnect between them. Then from the master, I want to put a byte of data onto the data port, so onto port 5. And then I'm going to take a couple of the pins on port 4 and drop them low. One is to say I've got data. So that's this, I'm going to do a chip select, basically tell the slave I've got data, and I'm going to drop an interrupt line on P42. So I'm going to use P44 and P42, and maybe for my current use case, I don't really need those two separate, but I believe that is how PIB is going to get used at some point here. So one is just saying I've got data, the other one is an interrupt line. And I suppose interrupts are optional, so maybe you wouldn't have to use P42 if you were doing polling or something like that, I'm not sure. Now, without PIB, there is no pin on port 4 that can do edge detection for interrupts, either a rising or falling edge. So that's a problem. Now, it must be that in the hardware for PIB that port 42 maybe has interrupt edge support, but that's not something you can programmatically work with other than enable or disable it, as far as I can tell. Being that that's the case, I need to somewhere get this signal to a different spot, whether I use IRQB or have something a little bit more dedicated to PIB, which I'm just going to use pin 64, which is a negative edge interruptible pin. So basically I've just, I put a jumper between pin 42 and pin 64 so that anytime my master drops pin 42 on its side, it's dropping it on the slave side. And that's also connected to P64. So that's essentially what's really triggering my interrupt, is P64 being driven from the master over to the slave. So at that point, then the slave runs its interrupt service routine, and it throws back a signal on P43 that says, okay, I fetched this byte. So it's got to fetch the byte off the data. It reads the data port. So, load A, port 5. And then it sends back an acknowledgement on P43 by dropping it low to tell the master, yep, I got it. Let's continue. And then there's maybe a few more things they go through, but at the end, P42, 43, 44 all get turned back to their idle values. So this would be all of them high. So P42, 43, 44 would be back to all high states. Now here's the actual interconnectivity that's on my I guess, my project that I've been working on the schematic for, this dual processor or dual 265 board. So you can kind of see how I've interconnected this. I put 33 ohm resistors between everything just to play it a little bit safe in case maybe the two different, both on the left and on the right, are trying to do something. Maybe one's trying to drive a high, one's trying to drive a low. I don't know, maybe this will protect me a little bit from myself. Those maybe are not needed at some point, and I'm guessing that they shouldn't be needed if this was designed in the hardware the way I think it ought to be. But I put them in there just to be safe. And what you're seeing is on the left, this would be my master essentially, and then on the right, this would be the slave, or what again I called this primary on the left, and I don't prefix it that way, but then the slave I try to prefix everywhere with AV underscore. So P42 to 42, 43, 44, 5, 6, 7, those are all direct connect along with all of port 5. Now P40 and 41 are your, NIMB and IRQB. So a non-maskable interrupt. Is it NMI? Maybe I had that backwards. But anyways, that's a P40. P41 is IRQB. I'm not using those for this, so those aren't on this picture. And then down at the bottom is where I'm showing that I'm connecting from my master here using the P60 over to the slave AV reset or RESB line. And then this very bottom is showing that I'm also taking this line 42 PIB from the AV and connecting it to on the same. So in this case, both of these connections at the bottom are on the same, the slave, the AV system, but just jumpering that 42 over to P64 for that interrupt. So like I mentioned, I've had some challenges. I could not get the hardware-based PIB working. Again, I think maybe that's two things. It could be that, yes, I shouldn't be writing to PIR3. I'm supposed to write to PIR7 for the data from the master to the slave. And or there was a hardware issue. Now on both the WDC board and my board, pins 43 and 44 are labeled this FA15 and AMS, and they're connected to the external flash from where I am running my code on both of those boards. Well, that's mapped to pins A14 and 15, and so those are pulled high, and they're normally always left high. But if all of a sudden I start writing to pins 43 and 44, like I drop 44 low, that just told the flash to jump to a different section of flash. And that will instantly halt my program. It'll stop it because it jumped to a different spot of flash, which is probably all Fs, and I'm not going anywhere at that point. So that's a problem. So what I ended up doing on both boards is I cut the traces to disconnect P43 and 44 from the external flash. And then I had to make sure I retain pull-up resistors, though, on A15 and A14. So I'm basically telling it out of the 128K external flash, I'm only going to use the top 32K, which was already the case. And I'm not going to be able to let there be some code that modifies FA15 or AMS to switch to different banks of that flash. And that's fine. I don't care about that. I just want my 32K program portion of that 128K. Because what was happening is when I was pulling 44 low, again, my system would just halt. So that obviously is not workable. So I had to electrically isolate my pins 43 and 44 from A15 and A14. And so on my design board, that wasn't so bad. Quick little trace cut. I left my pull-up resistors in place. And then I had to run a couple little bodge wires. On the WDC board, I didn't have an actual project file for it, so I can only see what I see for visible traces. And I don't know if it's just a 2-layer board. I don't think it is. I'm guessing there's more than that. But anyways, I did my best. I tried to trace out the tracks or the traces, cut the right ones. They didn't get the signal cut all the way. So then I had to track down from the flash side of things, cut those. That did get it disconnected, but then I lost my pull-up resistors, so then I had to solder on some pull-up resistors onto some of the traces on the board. So a little bit more hassle on that one, but I do have that basically updated also, so that A15, A14 are on pull-ups on both boards, and they are isolated from P43 and P44. So then what's next? I need to try the hardware PIB again, and I've removed again those flash ROM signals, which I know was causing problems. So that alone might resolve it for me. And also, like I mentioned, I was trying to write to this PIR3, which should do all the handshaking. So I'd say, here's my byte of data, write to PIR3. The slave should then be able to read and get that data, and all the handshaking was taken care of for me. But that wasn't working, and it could be that I'm supposed to use PIR7, not PIR3. That's all, again, stuff I need to find more information about, or just keep experimenting until I see the right activity on the control lines on port 4 when I try to write to one of these registers. Now, if I go over to the information, I do have, from the data sheet, let me zoom into this. I've got a blog post that I'm tracking a lot of this, but I took out all the snippets from the data sheet that are relevant to PIB. But here's one, for example, that just says that there are a series of these registers, and like PIR3, automatic handshake, and it says that is for the role of communicating commands or opcodes, PIR7, for communicating data or addresses between processors. I'm guessing you don't have to use it that way, but this is how it's set up. It doesn't necessarily say which one should be master, which one should be slave. Like master, you use 7 to write to the slave and use 3 on the slave to read it. I don't know. What I was trying, though, was to write to PIR3, and that was not working. So I am going to go try PIR7, and maybe that's the latest Copilot info is correct, that I should be using PIR7 and not 3. So that's something I just have to go in and experiment with. But I was already a long ways into this Pseudo-PIB, and I thought, no, let's just get Pseudo-PIB running. Then I'll come back and mess around with this hardware again. And like I said, I think these pins on the ROM were also part of the problem. So I mentioned, I've got this blog post that I'm trying to capture this information. I'll keep capturing information here, so you can check back there later. And then I thought I would just kind of get into maybe a walkthrough of what I have. So I'm going to get out of this and just bring this up here. So what you're seeing, 3 things. On my screen are 2 different TerraTerm windows. One of them is on COM3, the other one's on COM4. And if you look over here at my setup, one of them is going to the slave board right here, and one is going to the master board right here. So I've got a serial cable, I've got another serial cable, USB, I guess USB cable, but USB serial. So I can, from the master, write out to one of those serials. From the slave, I can write out to a different one. And what I'm going to do is I'm going to turn on my system, and as I turn it on, just keep an eye on these 2 windows. So basically the system comes on, and I've got some delays built in, but there's the master coming up, and you can see it says initialization complete. It says 265 at 10 megahertz, and I have my LCD and keyboard currently configured on it. The slave comes up and it outputs on its serial that, yep, I'm running at 3.6864 megahertz, and it's sitting there waiting. I've also, in the main loop of both of these, I toggle one of the pins, which is these red LEDs. So if I see those light up, that tells me it got to its main, and it's just sitting there looping at this point. So they're both sitting there and for all practical purposes idle. Now the test that I wanted to set up is that I could type a key, which is PS2 keyboard going into my master through this circuit, which I've talked about before, and that it would receive the keyboard input, it would write it out to its local terminal or serial output, just so I know it registered the key. But then it would use this PIB or Pseudo-PIB to connect over to the other board. The other board would get the IRQ, it would process the handshaking back and forth, ultimately read the data, and then send it out through its serial port. And so now if I come in here and I type, for example, an H, it shows up on my LCD, and it shows up on this screen here to the left saying that the master recognized it, and it showed up on the slave saying, yep, I got it too. So now, I can come in here and type in a bunch of characters. So there's hello. And for every character, then I'm sending that ASCII byte value from the master over to the slave. And so that's the exciting functionality I have so far. So obviously, instead of sending a character code, ASCII code, I could send a command followed by some parameter data, whatever it is I want to do, but I've got this private connection. And I'm using these ports here. So I've got my port 5, which just comes down here, goes through the resistors over to port 5, port 4, same thing, down to some resistors on the breadboard over to the other board. I have some debug LEDs. That's these black and white pair of wires going to the LEDs. Power is being pulled here from the breadboard to the slave. And then the slave also has a reset line and this extra interrupt line. So this would be my reset, this red, this brown going over there down to a reset. This yellow over here is an interrupt line on port 6 that is just simply jumpered over to one of these with a little pull up on that. But, I can now come in here and just type and do whatever I want to do. So there's my hello world. And that is all transferring just fine. So coming over here and looking at the code real quick, I've got this, and I'll have all this code posted when I put this video up. So if you go out to either my GitHub or my blog for this PIB, you'll find links to the latest code. But I've got the main code here, which I call this primary.asm. So it's 65265 primary. This is for the master, meaning primary. Here's the main code. So as this comes up, I'm configuring the MCU. So there's a procedure that does all my configuration there. I do a little bit of a delay just to let things settle, mostly the UART, so that I can now initialize the UART and start using it right away on a cold start. I initialize my VIA, versatile interface adapter, my LCD, my keyboard, and I jump to an init master PIB. And then that's it. Then I basically turn on interrupts and I sit here and just loop through main constantly. And every time I come through, I toggle port 64, which is just a status LED, and I see if there's any keys to process in a buffer. So if a key on the keyboard was pressed. Now on the PIB code, I just separated that out into a separate file, and so there's not a lot here, and I've actually got some of it actually over in the primary. So I'll jump through both of these real quick. So I defined some pins, pin 42, 43, 44 are ones that I'm using. And so that's my PII, which is really I have an interrupt, I've got data ready. I have a chip select that I pull low. So those two I pull low from the master. The slave writes back on this write enable that says, yep, I got the data. Let's continue handshaking, or let's continue handshaking, then read the data depending on how you write it. Init master, I then come in here and I say which pins are input and output for port 4. So this is my control port. So these bottom two would be my interrupt lines on the processor. So I don't want to be changing that. So I'll leave those as inputs. All the rest are outputs except for this line, which would be the input, because the slave is going to write back to that line saying, yep, let's negotiate this handshake. The data line is all output, which means on the slave it should be all input. There is a PIB flag register. I clear all that. I believe this is correct, that to clear it, it's like EIER, where you write a 1 to a bit to clear whatever's in that bit. So I'm loading this up, I'm clearing that. And then you have to actually enable PIB. And so there is an enable register. And so this is a flag register, then there's an enable register, and there's a bunch of different bits. The last bit is saying, do you want to enable PIB? And then there's some later bits that say, do you want to do manual handshaking or automatic handshaking? all that really matters right now, I think, is that I'm setting this to all zeros, but the last bit is saying don't even enable the PIB. Now, if I enable PIB, it takes over port 4 as far as I can tell. So then at that point, you can't control port 4. You can't write out to port 4 because basically the hardware is taken over that port. And you have to then use registers to control that port. Now, I could be wrong on that, but that's what it seems like how it's behaving. And if I was writing to this PIR3 and I'm supposed to be writing out to PIR7, that might explain a lot of the problems I was having, along with those 2 lines that were tied to the ROM. Then I set some initial values on these pins. So I bring up this line and this line, that is this PII and this chip select. So the interrupt and chip select, I pull those high because that's the non-activated. Those are active lows. So if they're high, they're not active. And then I let go of this line that I was holding the reset down. So over my primary, I kind of do the opposite of this. I pull down this pin 1 and basically have it pull down the reset line on the slave. And here at the end of my init of my PIB, or pseudo-PIB here, I free up that so that the secondary then can start up. Later in my main assembly, when I do press a key, and let's see if I can go just find this. This is where I pull the reset low right away when the computer comes up or the 265 comes up. But here, when I go process and I say, yep, a key was pressed in my main loop, it jumps into this code here called key pressed. And I send it to my LCD, plus I turn around and I send it over to this send PIB. And that send PIB then does this, and it comes in here and says, well, print it out to the serial. This is on the master, just so I know, A, this routine is running, what key is coming through. And then take this chip select and interrupt line low. That's what this is doing. And then it sits here and waits until the slave acknowledges it by dropping this PI web, which is the bit in between there. It brings it up high. And then once it brings it up high, I'm basically saying, okay, I'm good to go. I'm done. And let's get my values turned back up to their normal state. Now in the slave code, if I jump over to that, again, this is going to be things that say AV, audio visual coprocessor is my goal at some point. It's going to have a setup routine that I have to init the slave PIB. And same type of thing. So I'm going to go to port 5 and say that it's all input. I'm going to go to port 4 and say it's all input except for this line, which is this PI web line. I'm going to, let's see, it looks like I commented out the clear the PIB flags, but those could be put back in there. And then I am disabling PIB because, again, I'm not using the hardware PIB because I wasn't able to get that working previously. But maybe I can do that in this coming week is try to get back over to that and make that work again. And then if it's sitting idle, I want this PI web to be high. And when I do take it low, that's an acknowledgement back to the master. So its default state should be high. And then I need an interrupt service routine. And if I was using the hardware PIB, there's a handler and I can set up a vector that jumps to that or points to that, and I can show you what I think I've got that still in here. But I would have a vector that is for PIB specifically, and there is an address for that specifically of FF9C, and then so I could jump to this very specific handler just for PIB. But because I'm not using that hardware PIB yet, I am using this pin 64, this negative edge 64 interrupt that's going to go to FF98. But then I have that handler set up, and I think I left that here in my main right here. Yes. So that's this interrupt. I'll come right back to that. So ignore this one. I'm not using this one. And it's really just the setup, the init here. And then at that point, it's sitting, it goes back to, does its normal processing, looping in the main, whatever. But when the master drops that first signal for the interrupt, then this interrupt handler is going to run. And the first thing I'm going to do is when I get this interrupt, that means I know the master's already indicated to me, hey, I've got data on the data bus for you, go get it. Again, this is, when I say data bus, that's port 5 interconnected between the two microcontrollers. Go read it, print it out to the slave serial console, toggle this PI, basically this line here that is, what was it, 43, bring that low. And then at that point, it just simply waits for then the master to take its lines back up high. And then I can basically get out of here, clear the interrupt on the way out. So this is just a simple, negotiation between the two, I guess, as far as, how they're going to just make sure that one says I've got data, the other one says I've got the data and I acknowledge it, and then they both get back to ready state. So that's the code I have right now. Now, what it should be, though, at some point, when I go back to my primary, instead of me writing all of this code, well, it'd really be, this code on down and all of these waits, waiting for things. I should just be able to say, take something and store it instead of to PD5. I should be able to say, store it to PIR 7, let's say. And then all of this other handshaking just happens between the master and the slave. And on the slave, I would then have a PIB interrupt that would just simply read the byte. So that'll be simpler for sure if I can get that to work. But this is where I am today. So it's kind of acting like PIB hardware would act, I think. And it is working using those two ports. But I don't actually have the hardware working yet. I'm kind of faking it, fake it till you make it type of thing right now. But what I will do next is strip this code down again, go back to trying to write out to PIR 7, I think, and see if I can get that data byte to transfer and use the PIB interrupt on the slave and show that on the terminal output. So this is looks like I'm already over 40 minutes into this video. So this is probably where I'm going to, kind of shut that down. Again, I've got my master, I've got my slave, I've got direct connection between port 4 and port 5 between the two. I'm using a couple of extra GPIOs to manage a reset and deal with an interrupt because I'm not able to use the hardware PIB yet, along with some status LEDs. But I hit a key, it shows it on the LCD on the master, it shows it on the serial out on the master, transfers it to the slave then shows it on the serial output from the slave. And that is the extent of my pseudo-PIB at this point. But it's enough to tell me that the hardware now is working, and now I just need to figure out how to make the hardware do the work that I am currently doing through assembly code, because I think much of that can be offloaded to hardware, which has many benefits compared to my code. So stay tuned. I'm hoping in the next video I can show that hardware PIB is working, but I guess we will see.